Hello everybody. In this video I will explain game theory. Of course not all of it, but a large part of the amount of basic game theory covered in my introductory class. I will cover the notions of players, positions, moves, random moves, outcomes, payoffs, game tree, imperfect information, not backward induction, information sets, extensive form, expected value, normal form, weak domination, best response, pure Nash equilibrium, mixed strategy, brown fictitious play, and mixed Nash equilibrium. I made this video as a review of the material at the end of the semester before finals, but if you are mathematically sophisticated and patient, willing to stop the video and think or even look up certain concepts, you might at least get an idea of game theory in general. I will explain all these concepts at a very simple game. It is a variant of von Neumann-Morgenstern poker, played with only 12 cards. Each player just gets one card. I will explain the rules later. Even though the game is very simple and easy to explain and to play, I promise you that you will not play it successfully against me unless you have listened to my video. If I spend the night playing this game against a game theoretical innocent person, I will win a little money. The law of large numbers is on my side, because playing this successfully is just not obvious. There are simpler games, Meyerson poker for instance, or stripped down poker, where only one of the players gets a card. However, I think that most players will play these games in a way that even a sophisticated player will not win money on average. So in a sense it's the simplest, interesting game. Different to real-life games we all play daily, every mathematical game has rules, strict rules. The game we play is called VGM Poker 3-4-2-3. VGM stands for von Neumann and Morgenstern. John von Neumann and Oscar Morgenstern analyzed a similar game in their book on game theory published in 1944, thereby inventing game theory as a mathematical discipline. The number 3 means that we have cards only of 3 values, let's say jacks, queens, kings. The 4 means we have 4 for each, in total therefore 12 cards. The 2 and the 3 are the minimum bet and the raised bet. All these parameters can change, we will discuss a few variants later. Now how is it played? There are 2 players whom we call Anne and Baz. It all starts with a random move. Both players get randomly 1 card from the deck of 12 cards, 4 jacks, 4 queens, 4 kings. So there are 9 possible positions after this random move. What is a position? What is a move? And what is a random move? Now each player looks at her card, but does not see the card of the other player. In any of these 9 positions, Anne moves next. She has to decide whether she wants to check or to raise. When she checks, the game is over and we reach an outcome. Both cards are revealed and we have 9 possible outcomes based on the cards. The payoffs attached to these outcomes are as follows. The player with a higher card gets a minimum bet, 2 Swiss francs from the other. In case of a tie, no money is exchanged. If, however, Anne raises, then we arrive at the next 9 possible positions. In these positions, Baz has to move. She can either fold or call. In both cases, the game will be over and we arrive at outcomes. If Baz has folded, she has to give 2 Swiss francs to Anne, no matter what cards both have. In fact, Baz's card remains hidden to Anne in that case. If Baz calls, both cards are revealed and the player with the higher card gets now the raised bet, 3 Swiss francs from the other one. In case of a tie, no money is exchanged. The leading questions of game theory are: how should the player play if they want to win money? And also, how will the players play? Can we predict this? The timeline of positions and moves is visualized by a so-called game tree. Note that this is the timeline of the play as it is shown to a quiet observer of the game, who can look both Anne and Baz into their card. Positions are visualized by dots or vertices and the options are the lines connecting the positions. Positions where N has to move are colored red, Bass positions are colored blue, and the one random move position is colored in gray. Note that the options of a random move always have probabilities that add up to 1. They are written at the corresponding edges. In this case, 2 equal cards are a little less likely than 2 different cards. That's why we have slightly different probabilities at these edges. Outcomes, positions where the game is over and nobody can move anymore, are colored in black. And of course, to every outcome there are payoffs for the players N and Bass attached. These are written here. We can put a playing piece on a tree that will represent the present state of the play, tells the position we are presently in. The play always moves from left to right, starting at a unique starting position and ending at any of the outcomes. For instance, N might get a queen and Bass might get a jack. The play moves here. Now, if N checks, the game is over and N wins 2 Swiss francs. If N raises, Bass can fold, in which case she loses 2 Swiss francs to N too, or she can call, in which cases she loses even 3 Swiss francs to N. Isn't the reasoning now straightforward? Not at all. Be careful. The tree is not a description of the game yet. The tree shows what an observer who can see the cards of both players would observe. This observer always has full information in which state the play is. But the players don't have this information. If the play is in this position here, for instance, with both N and Bass having a check, N does not exactly know in which state the play is, because Bass could have a queen or Bass could have a king. So the play could be in this or in this position. This is called a game with imperfect information. For sequential games with perfect information, there is a very powerful tool, backward induction. Now, backward induction is not covered in this video because backward induction does not apply to these games. It does not apply to games with imperfect information. All positions for a player that you cannot distinguish are grouped into a so-called information set. That means a player to move only knows in which information set she is, not at what position. If N has a check, she does not know what card Bass has, so these 3 positions cannot be distinguished by Bass at the time she has to make a decision. So we have the first information set. The positions queen for N, check for Bass, queen for both, and queen for N, king for Bass forms another information set. And here's N's third information set. We can do the same for Bass. Here it looks a little more scrambled since the positions are ordered having N in mind, but the principle is the same. The game tree, together with these information sets, is called the extensive form of the game. It is a complete description of the game. Now assume both players are rather busy and cannot even come to the game. Instead, they write a secret email to the referee, telling her how they would play in every possible information set they find themselves. N might write something like, with a jack I would check, with a queen I would raise, with a king I would check. Bass might write something like, what I do when N raises, with a check I would fold, with a queen I would call, with a king I would fold. We see that both N and Bass didn't think this through yet, but they certainly have the right to play like this. The referee would insist, however, that both explain what they would do in every possible information set. It does not matter how likely the occurrence of that information set is. Such emails are called pure strategies, or strategies. How many pure strategies does a player have? Since the player is free to make a decision between all possible options in each of her information sets, the number of strategies is just the product of the numbers of options for every information set. N can choose between checking and raising in the information set where she has a jack, between checking and raising in the information set where she has a queen, and the same in the information set where she has a king. Therefore, she has 2 times 2 times 2 equals 8 strategies. They are CCC, CCR, CRC, CRR, RCC, RCR, RRC, and RRR. Where the first letter always refers to the information set of having a jack, the second for that with a queen, and the third for the king. Similar, Bass has 8 strategies: FFF, folding, 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 FFC, folding, folding, calling, FCF, FCC, CFF, CFC, CCF, and CCC, with the same ordering of the information sets assumed.